Hello students. So this question has been asked in the GATE 2024 control system. Okay. And this was from double E part. Okay. So let's see this question. For the block diagram shown in the figure, the transfer function they are asking, right? So input output relationship they are asking. So see, whatever complex block diagram they have given, you can always simplify by taking the variables. Here I am just concerned about the output and input, and I can consider any variable here, x, y. Okay, so you can do by any method. Okay, there are several methods. You can also go by Mason's formula, signal flow graph and all. So the most basic method to do this question is, you can consider this as c is coming here, output is coming here, right, and r is coming here. So this is minus c and this is plus r. So here this particular part I am getting as r minus c. Okay, and this particular part here, the output of this summer will become, because this here c is also coming to this feedback, but this is your positive feedback. Okay, this was your negative feedback and this one is your positive feedback. So here it is coming as plus c, and here it will be coming as minus of r minus c, minus of r minus c, right? So finally what I am getting here, so what will be this variable? I can see that if I consider this variable as y, so y into g will be equal to c, yes or no? And what is y? Y is c minus r minus c, right, into g is equal to c. So here I am getting c minus r plus c into g, and that is equal to c. So I'm getting 2c minus r into g is equal to c. So I have to get the input output relationship. So open the bracket, 2cg minus rg is equal to c. Now I'll keep r separate, so minus rg, and this part will go here. So c minus 2cg. Okay, so c I can take common and this will be 1 minus 2g, and here I am having minus rg. So what will be c by r? Because c by r they are asking the transfer function. So c upon r would be equal to minus g by 1 minus 2g. So that I can write it as minus g of s divided by 1 minus 2g of s. So which option it is matching? Option B is the, no, option D is the correct answer, right? Minus of gs divided by 1 minus 2 into gs. So option D is the best fit answer. Thank you. Hello students. So this question was asked from the control system part, and it was asked in EE, okay, electrical engineering. So in GATE 2024. So let's see this question. So consider the standard second order system of the form. So this is your standard second order system. This is your standard second order system transfer function, right? With the poles P and P conjugate, okay, P and P conjugate having negative real parts. So it is having negative real part. The pole location are also shown in the figure. So they have marked the pole location. So here I know that if it is a underdamped system, I am having the location of pole will be complex conjugate, right? So I know that it is given as S equal to minus zeta omega n plus minus j omega d. This is how you give the roots of the underdamped second order system, right? Because when the pole are lying in the complex plane, or when they are complex conjugate of each other, then this is what you get, minus zeta omega n, and this will be j omega d. And this part, if you see, this would be minus zeta omega n minus j omega d. right? So if you see here, okay, this part is omega d and this part is minus zeta omega n. Okay, and if you see, if I try to see the relation of zeta, zeta will be equal to cos theta. I hope you remember this. Okay, zeta is equal to cos theta, because this part is nothing but omega n under root 1 minus zeta square. So when you do this, you will get omega n here. So when you try to find cos theta from this triangle, so cos theta will be what? Cos theta will be the base by hypotenuse. So zeta omega n by omega n. So this part is coming as zeta. Okay. Now what is asked here? It is asked that omega system 1, they have given the value of omega n. So the omega n, that is radius of this semicircle, they have given, and theta value given. What is theta? Theta indicates the angle, okay, subtended by the complex pole with respect to the negative real axis. Okay, so the angle subtended by the closed loop poles with respect to the negative real axis, that is indicated by theta. And I have already got the relationship. Okay, this is nothing but omega d. Okay, this is your omega d only. So I am having cos theta is equal to zeta, and they are asking settling time. Now for second order system, the settling time is given as 4 by zeta omega n. They have not given the tolerance band. Okay, so I'm considering per 2% tolerance band. So whenever they don't give you, okay, the range or the tolerance band, always assume 2% tolerance band. So here they're asking which settling time is more. So if I consider system 1, so for system 1, the settling time will be 4 upon, what is zeta? Zeta is cos theta only. So that relation I'll put it here. So omega n into zeta, and zeta is cos theta. So that will be 4 upon omega n is 3 and cos 60. Cos 60 is half. So cos 60 is half. So it will become 8 upon 3. Okay. Now what about system 2? System 2, the settling time is, again, it is 4 by zeta omega n. So 4 by omega n into zeta. Zeta is cos theta. So just put it here. So 4 upon omega n for system 2 is 1 radian per second. And theta is cos 70. Okay, theta is 70 degrees. So cos of 70 degree. So here I am getting this particular part 4 by cos 70. So that will come out to be, so 4 upon cos 70 is coming out to be 11.69. And 8 by 3 is coming as 2.67. Okay, so you can check that system 2 is having more settling time compared to system 1. Okay, and you know that cos of 70, okay, will be less than cos of 60, because cos theta is a decreasing function. Without even evaluating this value, you can see that this is 4 by 3 into cos 60. So this part is higher, greater, and this part will be lesser, because cos 70 will always be less than cos 60, because you know that cos theta is a decreasing function. So if theta increases, cos theta decreases, right? So system 2 will have more settling time compared to system 1. So option B is the best fit answer. Settling time of system 2 is more than that of system 1. Okay. Hello students. So this question was asked from the control system part in EE 2024. Okay, let us see the question. Consider the cascaded system as shown in the figure. Neglecting the faster component of the transient response, which one of the following option is a first order pole only approximation such that the steady state value of the unit step response of the original and approximated system are same. So this part is based on dominant pole concept. Dominant pole concept. I told you that this particular concept, okay, is used for reducing the higher order system into corresponding lower order system. And before reducing, you must convert the system transfer function in a time constant form such that the steady state value of both the system, that is the original system and the reduced system, remains the same. Or I can say the DC gain of both the system, the original system and the reduced one, must be same. Okay, so here I'll be using this particular concept. So my transfer function, that is output by input, say this is C, this is R. So C upon R is given as this particular gain are cascaded. This particular two blocks that are given are cascaded. So their gain will be multiplied. So their gain will be multiplied. So this will become S plus 40 divided by S plus 1 into S plus 20. Right? Now, I know that here, if I draw the pole zero map, so the dominant pole is -1, S equal to -1, because -20 and -40 are lying far away. -20 and -40 are lying far away compared to this particular pole. So their transient will die out quickly. Their transient will die out quickly. So this will not have any significant impact. These two poles will not have any significant impact on the transient analysis of overall system. So I can neglect these two poles. Okay. But before reducing, I must convert my transfer function in the time constant form. So this part will become 1 plus S by 40. This part will remain as it is, 1 plus S. And again, 20 I'll take common, 1 plus S by 20. So now I am getting the time constant form. Here the time constant is 1 by 40. Here the time constant is 1 by 20. Here the time constant is 1. So you can see that the time constant of this part and this part is very, very less. Okay. The time constant of this part and this part is very, very less. Here the time constant is 1 by 40. Here the time constant is 1 by 20. So their transient will not last long. Okay. Only this pole will have significant impact. So I can consider this pole as dominant or significant, okay, in the transient analysis. So now I am ready to remove it. So 20 to the 40, and I am able to remove now this pole and this pole. Remove it, remove it. This is what dominant pole concept says. So I am getting 2 divided by the leftover is 1 plus S. So my approximated or the reduced, okay, so here I am writing, so C by R that I am getting is 2 upon 1 plus or S plus 1. This is the reduced system, okay, reduced transfer function, and this was your original transfer function. Now you can see that the DC gain of both the system would be same, because if you put S equal to 0 here, okay, the DC gain will be 2. The DC gain here is 2, because 2 by 0 plus 1 is 2. And here also if you put S equal to 0, so 40 divided by 20 into 1, it will be 2 only. So here also the DC gain is 2. So for the original system or original transfer function, DC gain is also 2. And for the reduced system or the reduced transfer function, DC gain is also 2. So the best fit option is option B, that is 2 by S plus 1. Okay. Hello students. So this particular question was asked in GATE 2024 control system. Okay. So this is a control system question. So here they're asking that consider the closed loop system shown in the figure with GS equal to this k s square minus 2s plus 2 and s square plus 2s plus 5. So complex pole is there, complex zero is there, right? So angle of arrival will also exist and angle of departure will also exist. Now what they are asking here, the root locus for the closed loop system is to be drawn for k ranging from 0 to infinity. The angle of departure between 0 and 360 degree of the root locus branch drawn from the pole minus 1 plus j2 in degree is. So what they're asking, angle of departure they're asking for this particular pole. For this particular pole, they're asking you the angle of departure. Okay. And k is ranging from 0 to infinity. So it is a root locus question. And here I'm having complex 0. So it will be having two roots. What are the roots here? So it is having two roots. S1 will be equal to, suppose if I try to find this, so s equal to minus 2 or minus minus plus 2, it will be plus minus. So if I try to find it here, okay, so s will be equal to minus b, that is plus 2 plus minus under root b square minus 4ac. So 4 minus 4ac. So 4 into 2 is 8 divided by 2a. A is 1. So I am getting 1 plus minus 4 minus 8 is minus 4. So that will be j2 and j2 by 2 is j1. So I am getting s equal to 1 plus minus j1. So the complex 0 are 1 plus j1 and 1 minus j1, right? And the complex pole is also given. So what are the roots of complex pole? So here minus 1 plus j2 already they have given. Okay. So one of the pole would be minus 1 plus j2 and the other will be minus 1 minus j2, right? If you want, you can find it also, but no need, because already they have given that you have to find the angle of departure for one of the complex pole. So if one pole is minus 1 plus j2, the other will be complex conjugate of this. So minus 1 minus j2. Okay. So now I'm ready to draw the pole 0 map. So if I draw the pole 0 map, it will be easier to understand this angle of departure. So the zeros are lying at 1 plus minus j1. So 1 is here and j1 is here. So this is 1, this is plus j1 and this is minus j1, right? This is plus j1 and this is minus j1. Now the poles, the complex poles are minus 1 plus j2. So minus 1 will be here and plus j2 means somewhere here. So I am having two complex poles. So here I was having complex zeros and here I am having complex pole. Okay. So this is your complex pole. So minus 1 plus j2 and minus 1 minus j2, right? Now if I have to find the angle of departure for this minus 1 plus j2, okay, if I have to find the angle of departure for this minus 1 plus j2, what I can do is I can join this particular pole. Okay, for this pole they are asking, right? For this particular pole they are asking angle of departure. So I can join it with all the poles in 0. So for this pole I am joining like this. For this 0 I will join like this, and for this 0 I'll be joining like this. Okay. Now I have to take anti-clockwise angle. If you're taking anti-clockwise angle for one, you have to take anti-clockwise angle for all the poles and zeros. So this particular part will also be, so I'm taking anti-clockwise angle, so this is plus 90 degree, okay, because I'm taking anti-clockwise angle. So here also I'll take anti-clockwise angle, and you can see at that it is greater than 90 degree. That is, this particular part is 1. Yes or no? Because this particular part was J1 and this is J2. So the magnitude will be 1 and this magnitude will be 2. The distance between -1 and +1 is 2 only. So this part is 2. So this will be, say, this is phi Z1. Okay. And this particular part, if you see here, this also anti-clockwise angle I'll take. This will be phi Z2. This is also greater than 90 degree. That means the angle would be lying in the second quadrant. Okay. So here, if you see, the distance between this pole and this zero is how much? It is 3. Okay. Because this particular part is J2 and this is J1. So 2 plus 1 is 3. So this particular part would be 3 and this will remain 2 because the distance between -2 and +2 is 2 only. Okay. So now I can calculate all the angles. So here, this particular part was phi p1 because there is only one pole existing. Okay, phi p1. Okay, so for if I have to calculate the angle of departure for this pole, so this will be your angle corresponding to 0. Okay, phi z1 and phi z2, and the angle subtended by the other pole would be phi p1, right? So now what I can do is, I know that phi d is calculated as 180 degree plus phi, right? And phi is given as the angle subtended by all the zeros and the angle subtended by all the poles, right? Now let us calculate this angles. So what will be phi z1, guys? The phi z1 will be equal to 180 degree minus tan inverse b by a. So 1 upon 2. So 180 minus tan inverse 1 upon 2. Okay. What will be the value of phi z2? So phi z2, it will be 180 degree minus tan inverse. This part is 3 and this part is 2. So what is this angle? This angle would be, total is 180 degree minus this angle. And this angle is nothing but tan theta will be equal to perpendicular by base. So 180 minus tan inverse 3 upon 2. So 3 by 2, right? And phi p1 is already given as 90 degree. Okay. This is phi z1 and this was phi z2. And this phi p1 is nothing but plus 90 degree directly, because you can see that from if the angle is taken in the anti-clockwise direction compared to the positive real axis. Here also I am taking the angle with respect to positive real axis, positive real axis, positive real axis, and all the angles are anti-clockwise. Okay. Now I know phi p1, phi z1 and phi z2. So this summation of phi z, it will be phi z1 plus phi z2, and summation of phi p will be just phi p1. Okay. Let's go to the next page. Now here phi d, I know that it is 180 degree plus phi, and phi is, you are getting it as phi z1 plus phi z2 minus phi p1. Okay, phi z1 you calculated it as 180 degree minus tan inverse 1 by 2 plus, again phi z2 is 180 degree minus tan inverse 3 by 2 minus phi p1 is 90 degree. Now if you calculate this angle, let us calculate. So I can write this as 360 degree. Okay, 180 plus 180 is 360 minus tan inverse 1 by 2 minus tan inverse 3 by 2 minus 90 degree. Let us see what you are getting. 360 minus tan inverse 1 upon 2 minus tan inverse 3 upon 2 minus 90 degree, right? So you are getting as 187.12. This is phi that you are getting, 187.12. So therefore, phi d will be equal to 180 degree plus phi. So phi is 187.12. So this is what you are getting, 367.12. So phi d, because you want angle in between 0 to 360 degrees. See here, they have already mentioned that the angle of departure should be between 0 and 360 degree. So I can write this as phi d equal to 360 degree plus 7.12. Now 360 degree is nothing but 0 degree, okay, because both are positive real axis only. Okay, this you are telling it as 0 degree. If I just take one anti-clockwise angle full rotation, it will be 360 degree. So both are same. So this is equal to 7.12 degree. So the angle of departure that you are getting is 7.12. Okay, so this is your angle of departure. Hello students. So this particular question was asked from the control system from GATE EE 2024. So in this question they are asking that consider the stable closed loop system shown in the figure. The asymptotic Bode magnitude plot of GS has a constant slope of minus 20 dB per decade at least till 100 radian per second, with the gain crossover frequency being 10 radian per second. The asymptotic Bode phase plot remains constant at minus 90 degree at least till omega equal to 10 radian per second. So they have given you the information about the magnitude plot and the phase plot of the Bode plot, right? So the magnitude plot and the phase plot they have given. So in the magnitude plot, what they are telling is this is magnitude in decibel versus log base 10 omega. And if you see here, the magnitude is 0 along the x-axis, because you know that the y value is equal to 0 along the x-axis. So this axis is also called as 0 dB axis. 0 dB axis. Okay. And the phase plot, so this is your magnitude plot, and this particular part is your phase plot. So in the phase plot, what they are telling is that first of all, magnitude here they have given that it is the magnitude plot of GS has a constant slope of minus 20 dB per decade at least till 100 radian per second. So till 100 radian per second, okay, 100 radian per second, they have given you the constant slope, which is minus 20 dB per decade. So they have given you information about the initial slope, okay, and they are asking you the steady state error for unit ramp, okay. And here the phase plot they have told that it remain constant at minus 90 degree. So it is minus 90 degree till omega equal to 10 radian per second. So here this value is minus 90 degree and this is 10 radian per second. How I came to know that this particular point indicates 10 radian per second? See, they have already given that the gain crossover frequency is 10 radian per second. what is gain crossover frequency? The gain crossover frequency is the frequency at which the magnitude plot cuts the 0 dB axis. Okay, I told you that it is the frequency at which the magnitude of the open loop transfer function becomes 1, or I can say that it is the frequency at which the magnitude plot will cut the 0 dB axis. So the magnitude plot cuts the 0 dB axis at this frequency. So this is your omega GC, gain crossover frequency. Okay, and this is given as 10 radian per second. Now you know that the initial slope has been given. So the initial slope is minus 20 dB per decade. Okay, so this indicates that the type of the system is 1, and for the type 1, you know that type 1 system and unit ramp input they have given. So given input is unit ramp. So you know that for unit ramp, okay, the kV value, that is velocity error coefficient, will be finite, and hence the error will be finite for type 1 system. Okay, if you remember that for type 0 system and unit step input, Kp and error were finite. For type 1 and unit ramp system, Kv and error were finite. And for type 2 and unit parabola, Ka and error were finite. Okay, so here I know that this particular part, okay, is your Kv, because for type 1, if the system is type 1, then the first intersection, okay, the first intersection of the plot, first intersection of magnitude plot gives Kv is equal to omega. So this omega is nothing but Kv. Okay, therefore the error will become, the error will be finite, and Kv is, you know, the value of Kv, which is equal to omega, and that is equal to 10 radian per second. So this error will be equal to 1 by Kv, because they have told you that it is a unit ramp. For unit ramp, the error formula is 1 upon Kv, and if it is ramp of sudden strength or input, so A by Kv. So 1 upon Kv means 1 upon, what is Kv? 10. So it is 0.1 units. So this is 0.1. Hello students. So this particular question was asked from the control system from GATE EE 2024. In this question, they are asking that consider the stable closed loop system shown in the figure. The magnitude and the phase value of the response, the frequency response of GS are given in the table, full stop. The value of gain for a 50-degree phase margin is, okay. So this K1 value they are asking. Okay, this K1 value they are asking. So what is the known information? They have already given the table, but remember, this is not for the, this table is not for the entire system. Okay, this table is given for this GS. Okay, the magnitude and the phase value of the frequency response of GS are given in the table. Okay, this particular magnitude and the phase values are given in the table, and the known information is only that the phase margin is 50 degree. Okay, so phase margin, it is equal to 50 degree. I know that phase margin is given as 180 degree plus 5, so that is equal to 50 degree. So 5 will come out to be 50 minus 180 is minus 130 degree. So this 5 is nothing but 5 GC. This is 5 GC, because this particular phase is nothing but the phase at gain crossover frequency. right? So this is for entire system, because 50 the phase margin that they have given is for this entire system. Okay, so what is the total angle? The total angle, the total phase of this overall system. See, I'm having the overall phase as for K1 by S. I can write for this I am having minus 90-degree phase, and for this I am having phase of, say, angle GS. Okay, so that is equal to minus 130-degree. Okay, so minus 90-degree plus angle of G of S is given to you as minus 130-degree. Now here this particular angle was given at gain crossover frequency. So this particular value that you will get will be your the angle of GS at gain crossover frequency. So the angle of GS is coming out to be minus 130 plus 90, that is minus 40-degree, right? And this particular angle that they have given is here. Okay, most of the students, what they will do, they will mark it minus 130. So for corresponding to minus 130, they will consider that the gain crossover frequency will be 2. No, this particular table is given for GS only, but I have to calculate the angle of GS, because whatever phase margin that they have indicated is for the overall system. Okay, so the 5 GC that I'm getting here is for the overall system. So the phase at gain crossover frequency that I'm getting here is for the overall system. So minus 90-degree plus angle of GS, that will be equal to minus 130. So angle of GS, now I got minus 40-degree. So corresponding to this particular angle, now you have to check the table, because now you know the phase of GS is known to you now. Okay, this was not the phase of GS, this was the phase of overall system. So the phase of GS is minus 40, and here the omega is given as 0.5. So this is the phase of GS at gain crossover frequency. Remember that, because see, the phase of the GS can have any angle at different value of omega, but specifically at this gain crossover frequency, I'm equating the angle. So this phase of GS, which is known to you, is for this particular frequency, that is omega GC. So omega GC is known to you as 0.5 radian per second. And what is the magnitude of this GS? So magnitude of GS is given to you as minus 7, because they have given the magnitude in dB. They have given the magnitude in dB. So first I have to calculate this particular part. Okay, the absolute value of the magnitude. Now the magnitude in dB is known to me, and that is minus 7. So I can convert it into the absolute value by just using 20 log base 10, the absolute value of GS. Okay, here the GS was given, but the GS was given in dB. This is the GS value in dB, right? So now the absolute value of the magnitude that I'll get is minus 10 to the power minus 7 by 20. So 10 to the power minus 7 by 20 will come out to be minus 7 upon 20. So the absolute value of the magnitude, I'm getting it as 0.446. Now you know the absolute value of the magnitude for GS, and here the absolute value of this particular block will be K1 by omega. Yes or no? Because for this particular, say this block is G1S. So G1S is given to you as K1 by S. So K1 is given. So this particular value, if you just try to find out the magnitude, so first I can have G1 of j omega. So that will be K1 by j omega. So the magnitude of G1S, I'm getting it as K1 by omega. So the magnitude of this is known, and the magnitude of GS is known to you, right? Now I know that at gain crossover frequency, let me go to the next page. So at omega equal to omega GC, which is known to me, that is 0.5 radian per second. I know that the magnitude of overall system, okay, the magnitude of overall system would be what? Would be equal to 1. So here G1, this magnitude of overall system means magnitude of this and magnitude of this. So magnitude of G1S and magnitude of GS, absolute value, okay? Absolute value of G1S and the absolute value of GS, that is equal to 1. So absolute value of G1S is K1 by omega, and the absolute value of GS is 0.446. That is what you got now, 0.446. So now I will equate it to 1, and omega is known to me. Omega is nothing but omega GC here, because at this particular frequency only the magnitude will be equal to 1. The magnitude of overall system would be equal to 1. So the K1 value that you will get is omega GC by 0.446. That is 0.5 by 0.446. So the K1 value that you will get is 0.5 divided by 0.446. That you are getting it as 1.12. 1.12. Okay. So here the value of K will be equal to, you can write round it off to 2 decimal places. So you can write 1. Okay. The overall value is 1.12. Okay. They will give you the range for that. No need to worry.